Dr. Chen cannot be here, so he asked me to host today's conference. So today we will have Dr. Simone Silvestri to give a talk on internet agricultural things. And thanks for industrial partners to sponsor and provide feedback for us.
Thank you. Thank you very much, Nick, and thanks everyone for coming. So today I'm going to give you a little overview about some research going on the domain of smart farming and some problems specifically that me and Enrico here, my PhD student, has been working on. So there are a couple of projects on these topics that are funded by the NSF and NIFA, and these are collaborations with some colleagues here at UK, as well with the Iowa Soybean Association, Missouri Science and Technology, Iowa State, and Missouri University. Okay, so first off, why do we need...
One question. Could computer science help this generation farming, or only the next one?
It's always better to say the next. So why do we need smart farming? Well, there are several reasons. Probably one of the main ones is that the world population keeps growing. And here you have a little graph that shows over the years how the world population is expected to grow, reaching about 10 billion of people by 2025 or some 75, etc. So there are some forecasts that believe that we need to increase agricultural production by 70% by 2050, which is a very difficult goal to achieve, as you can imagine. It's also hard to find skilled laborers that can work in the field and can also run some of the complex machinery that are used in farm agriculture. Also, the cost for farmers is going up, and of course this reduces the margin for profit, and so it's important to be more efficient in delivering and growing the products, whatever desired animals and non-animal products, in order to deliver to the user, essentially to the final customers, and of course make also the farmers able to have a living and live a decent life. And there are a lot of economical implications here that I'm not going to touch about the size of farming changing over time. There are large owners that own most of the farmland in the US and abroad. These are other things that have nothing to do with economics. But anyway, farmers are definitely struggling, and they have a need to increase productivity in order to keep profit and at the same time deliver a high quality product, because today customers are increasingly aware of the quality of a product, and the demand is actually shifting towards higher quality products. And at the same time, also for the animal side, there is an increase aware about animal welfare, and so we really tend to buy, anyway, there is a larger fraction of population that tends to buy products that come from animals that have been treated more fairly during their life on the farm. And so there are all these pressures that go into the farming business, and so smart farming in general can try to improve the productivity and try to address some of these challenges. So first of all, let's try to look at what is available today, and also to try to understand, where research starts and what is actually currently available. And this is one of the challenges that I would like to try to highlight in this talk is, when you do this type of interdisciplinary research, so where do you really, draw the line? Okay, now I'm doing research, or maybe I can just go and buy this product, at the store now. So, maybe many of you, as myself before, I wasn't really aware of what was going on, and so let's just give a little overview of what are the products that today farmers can use, and also some research development. So first of all, if today you step into a tractor, it looks much more like you are driving an airplane rather than a tractor. You see all these different screens, GPS, satellite, internet connectivity. So these tractors are actually driven semi-automatically, which means that they are positioned by a GPS, and the GPS decides where they need to turn. So for example, here, if they are spreading some nitrogen or pesticides or some sort of nutrient from the plants, what you want to avoid clearly is the overlap between, when you're moving in this direction, then you turn, you move in the other direction. If there is some sort of overlap, then you are treating those plants twice, and you are also wasting products, right? Really something that you don't want to do. So the GPS here can actually help you do this turn very accurately and prevent and reduce this overlap almost to zero. And also, you can design different areas of the field to be treated differently. And so this sprayer actually adjusts the amount that they are spraying depending on the position that the tractor has in the field. So that there is definitely a very big technological advancement that we see today in this type of machinery used in the farms. At the same time, there is an increasing use of sensing technologies. And here we're talking about sensors on the ground or kind of robot sensors that can actually move around the field, or even unmanned vehicles that can fly and take images. So for example, ground sensor can take information like humidity, pressure, or weather data, etc. Or this type of robots may be used to take pictures of the plant leaves, and sometimes these are used as hyperspectral cameras, which generate very, very large file sizes, and then this can be analyzed, for example, to understand if a leaf is going through some sort of water stress or not. And this can be used as input to the tractor that we saw before, or to some smart navigation system to decide how much water to deliver in different parts of the field. And of course, similar information can also be taken today by unmanned vehicles. Of course, there are challenges due to positioning, due to the reduced resolution, due to the fact that you are high in the sky, and also the fact that the picture that you take will overlap. But there are definitely several applications today of unmanned vehicles. And again, this is not research. I mean, when I used to work on a project back in Missouri a few years ago, there was a guy that actually owned a company that would come to your farm, come with this big drone, pull it out, take the pictures for you, and then analyze it, and then give you back the results. Were you there at that time? Ricardo was working on that, right? Yeah. Anyway, so there are already commercial solutions for this. Okay, so there are of course research that can be done, but there are also a lot of things that have turned into commercial applications. So there are still several questions. So first of all, that involve computer science. So one of the first ones is, where do I do the computation? Because here you have, data of different sizes. Could be some small data, like for example, what is the humidity in this spot, or could be also large hyperspectral images, which is generated in the middle of an agricultural field where generally you do not have internet connectivity. So where do you do the computation? Well, it depends. It's challenging. It depends on what type of computation you want to do, right? If you want to run a big, deep neural network, then maybe your drone may not be available to do it. And so what my colleagues, for example, in Iowa do, they collect these type of images with their drone, then they get the drone to the base station on the side of the field, they put the images on a USB drive, they take their car, they drive back to the lab, they plug it in their computer, they transfer to the cloud, and then they run the deep neural network. So it's kind of inefficient. So of course there could be advancement that could be done in order to try to make this process automatic, try to use, for example, some more distributed computation, such as edge computing or even local computation on these smart devices. Of course, the challenge is trying to preserve the same type of accuracy that a big neural network run on the cloud could have. There are also some new wireless technology that could be used to try to transfer this data over long distances. And one of them, probably you have heard of it, is called LoRaWAN, that reuses the deep white space in order to achieve kind of a low data rate over long distances, similar to what a TP type of transmission would do. And today also there are several commercial applications of LoRaWAN. You can actually buy your little LoRa gateway and devices and connect them and use them in your applications. So this could be a potential solution for at least certain types of data that is collected, and the main limitation here is the limited data rate that you have, but you tend to have, a transmission range of several miles, sometimes even 10 or 15 miles as well. So it could definitely help transferring this data from where it's generated to where it could be processed. And of course, as you may imagine, there could be some privacy concerns of farmers, so you may use some sort of federated learning, or also distributed machine learning, so you split the model in different pieces and then you try to recombine it in a central location as well. Another product that is available today on the market are sticky traps, and IoT-enabled sticky traps. So what are these? They look more or less like this. Here at the bottom, they have a very sticky surface, and insects can go through these little holes, then they touch the bottom, and they get stuck there. And so what you may see, and so at the top here, so there is a camera, and the camera takes periodic pictures. And these pictures are sent to a little SIM card that is here up to the cloud, and the cloud does the object detection and recognition, which means that it takes this picture, it splits it in little objects that it wants to identify, and then it tries to identify what type of insect those are. And why this information is relevant, because the farmers want to know if there is a current infestation of a certain insect, and especially they want to know it at the start so they can treat it at the right time. And here also there are interesting economical implications, because basically it's not always convenient to treat at the beginning, so the function that relates how the productivity is affected by the number of insects that are present is not straightforward. It's kind of a discontinuous function, or anyway, it's not a simple linear function. So if the infestation stays at a lower level, then maybe you don't need to treat, but then if you start seeing an increase, then maybe you need to treat before it reaches a level that the productivity of that crop drops significantly. So it's hard to actually measure these things and decide when to intervene, but definitely a tool like this can give you a lot of information. Because this camera takes pictures periodically, it performs the machine learning periodically, it also can also give you over time how that population of insects is evolving. And so you may get out of your interface something like this that tells you, over time, what are the number of certain animals, certain insects that are detected, and you can decide what to do with it. And again, this is a commercial product. It's called Spice Scout, and everybody can buy it. So it's a nice application of machine learning and Internet of Things devices. In terms of research, also there have been some colleagues that recently have looked at trying to identify if a leaf is going through some biotic stresses, or basically a disease, and particularly they look at 3 of them: minor, FOMA, and rust. And I don't remember what type of foundation this was. Doesn't matter. So basically here they try to use a deep neural network that takes as input the image, and then it tells you, oh, this is a healthy leaf, it's a leaf affected by minor, by FOMA, by rust, etc. And one of the challenges that is very common, and I'm going to stress it also later into this talk, is that here we very often deal with very small data sets. Because these are pictures that are taken often by humans, and an expert needs to look at this picture and say, okay, this is a minor, this is a healthy leaf, this is a FOMA, this is a rust, and so on. So how many of these you can actually make? Maybe 1,000 is already a huge work. And similar is something that, similar constraint is what we have in the research part of the talk that we're going to have today. So what they try to do in this paper is actually try to use some sort of augmentation in order to, for example, rotate the images, modify the images, modify the light exposure, etc., in order to start from a smaller data set and try to generate a bigger data set that can be used to train the machine learning models and then use it in the field. And they seem to be pretty successful at it. But of course, it's something you can do only in certain contexts, and the scalability is still kind of a question. Anyway, in order to conclude this part, I just want to stress that precision agriculture, smart agriculture, is expected to keep growing for the reason that I mentioned at the beginning. There are a bunch of market studies that show that there is going to be an increased amount of investments and growth of the smart farming technologies that are going to be used in the farms. And I mean, this is kind of intuitive, and we see it in every aspect of our life, and of course, farming is not an exception. So let's try to move a little bit closer to what we are doing. So I've been mainly stressing about and talking aspects related to crop farming. But well, we can try to use these Internet of Things technologies also with animals. And there are today's technologies that probably some of you are not aware, that you can equip, for example, a cow or another type of farm animal with accelerometer, with a GPS pointer, with microphones, RFIDs, automatic feeders, automatic scales, cameras, etc. that may look like something you can see here in these pictures. And so what do we do with all this information? Well, we can use the data that comes from the sensors. And again, these are devices that you can buy today. Okay, so there is still no research involved. So, for example, we can know how many steps a cow takes, what is the laying time, laying pulse, what is the motion index, that basically tells you how much a cow is moving during the day. Also the feeding behavior, how much milk it drinks from the feeder, what is the drinking speed, what time, how frequent, if it finishes whatever he's eating or if it doesn't finish whatever he's eating, etc. So all this sort of information can be collected. So it's sort of having an extended Fitbit for a cow. Okay? Well, of course, one may think, okay, but so what? I mean, who cares about knowing what a cow is doing and how many steps it's taking? It's not like us, you know, like today, hey, how many they do 6,000 cows. Well, there may be some useful things that we can do with this information. And this is what we are trying to do in our research. So, for example, there is this disease, which is called the Bovine Respiratory Disease, or BRD. It's a huge problem for dairy cows. So this is the second leading cause of disease and death in young dairy cows. And also it's the cows that, basically young cows are the largest investment for a farmer. So there's a big economic loss due to the fact that illnesses like this, and specifically BRD, affect the cows in a farm. And then of course, once one cow gets it, then this can spread to other cows, and so you can have an outbreak and even a more significant economic loss. Additionally, it is expensive to diagnose. It affects the growth of a cow, so eventually it will produce less milk than it would have produced if the cow was healthy to begin with. So you get also reduced long-term performance from the cow. So definitely this disease is a big issue and affects the economic profit of farmers and generally reduce productivity. It is also a multifactorial disease which is difficult to detect. So it requires a lot of it shows a lot of different symptoms, like abnormal eye and nasal discharge, a certain head tilt, coughing, elevated temperature, ultrasound. So clearly you need a vet in order to come to the farm, visit your cows, and tell you if the cow is or is not sick. And this, of course, is expensive. I mean, you need to pay the vet by the hour, and you have a lot of cows in your farm, right? That's why you have one. It's not a pet. So, of course, it's a big investment to have a vet come and check if your cows are sick. And you can do this only every so often. Additionally, if you don't treat it immediately, then the performance of the cow will decrease significantly over time. And also there is a chance that this will turn into a chronic disease. So it means that the cow is never going to recover from it, and it's just going to have it for a very long time.
So what causes it?
I think
viruses or
it's a virus or bacteria. You don't know. I think it's a virus. Yeah, like our, it's sort of our pneumonia, more or less. But then it can turn into a bacterial infection, so you need to do the antibiotic treatment. So, how can we try to help? Well, the idea is to use all this information that we can collect from IoT devices, such as accelerometers, GPS, automatic feeders, etc. Use this to train a machine learning model that will provide information to tell you if this cow is sick, or even better, if this cow is getting sick. And I'm going to discuss what this means later, in order to help vets do their diagnosis, and ideally one day maybe do the diagnosis without the vet. So this is kind of a futuristic view, but the idea is to for now corroborate what the vet can tell you, or tell you if this is the case of getting the vet from the farm, or potentially start the treatment before even the vet can tell you that the cow is turning sick. And so some of our results actually show that we can tell that a cow is getting sick even before it's actually diagnosed as sick. So there are some real works in this topic, and there's not really much that tries to use machine learning and Internet of Things to do that. So there are some statistical studies that show that there is a correlation between change in behavior and BRD. So this is a good motivation to say, oh, maybe we can use these devices that can detect what the cow is doing to see if there is a change in behavior over time and say, oh, okay, maybe this cow is getting sick. There are some approaches that just try to use statistical inference, so not machine learning, and they achieve similar results than what you get basically with a pet coming there in terms of how often, how earlier you can detect the disease. And there is one only approach that uses random forest to do that, and different from us, as I'm going to mention in a few slides, it doesn't really look at the cost of different features. Anyway, we compare to this approach in order to see how we perform with that. And there is some research in terms of cost-sensitive feature selection, but we use models which are generally pretty abstract. In some application in the medical field, there's no application in such an animal domain like we are doing. And I'm going to mention the reason why we focus on this cost-sensitive feature selection. So before we do that, I want to give you an idea of the huge work that our colleagues in animal science have done here to just collect the data. Okay, sometimes us as computer science, scientists, we are used to go to the internet, download that data set with thousands of data points or entries, or even millions of data points or entries of labeled data, but this is really hard to do when you deal with real cases, or for example, like animals in a farm like here. So here, our colleagues have observed 106 cows over 50 months period. During this period, they went to the farm every day to perform vet exams. Okay, so you can imagine the amount of effort to do that. So out of this 105, 106, 54 developed BRD over this time, and for each cow they collected what we call automatic features, so basically features that can be collected by IoT devices, such as, for example, activity behavioral data with this accelerometer that tells you the total step count, the line time, line pulse, motion index, etc. The feeding behavior with the RFID attached to the left ear. Here is a feeder, you can see. And it tells you there are two types of feeders, one for milk, one for grain. And of course, the feeder recognizes the cow, and then it tells you, for example, what is the milk intake for this day, what is the percentage of milk consumed, the daily average drinking speed, etc., etc., etc. So a lot of these type of features that can be collected automatically. And also the temperature data of the farm that would be different from outside, and also some data of the weather in general. So this is what we call automatic features, so automatic information that can be collected from IoT devices. But then they also did basically what we would call the ground truth, right? Because we want to know if these cows were actually healthy or sick on a certain day. In order to do that, they did health exams, again, every day or almost every day, as much as I remember. So in order to do that, you need to apply this procedure, which is called the Wisconsin scoring system, that basically give a number to each of these symptoms, depending on how severe it is. And then if you're above a certain threshold, then they let's say, okay, you have BRD, otherwise you don't have BRD. And here there are some examples of what this means. They also perform, of course, they weigh the cows every day using the scale, and they also perform a lung ultrasound. Can you imagine how long it takes to an ultrasound of 106 cows? Just anyway, and they collect all this in order to build what the ground truth is. And this is just for 106 cows. Okay, so in order to label if that day the cow was sick or it wasn't.
So question, how often do they ultrasound a different cattle?
I think it's like cover.
It was, so the health exams were done every day, with an ultrasound once every 3 days.
So, can I take a side note here? So Wisconsin cattle are generally dairy, right? So one of the things farmers have done for 100 years is measure the production of the cow, right? So they just, how many gallons of milk do they produce? When they don't produce as much milk as what they have been expecting, they start to get unhealthy. They ship them to Kentucky to feed on the bluegrass to refresh the cattle's production capability. So
That's it.
this land grant university is uniquely located to handle these things.
I didn't know.
So, what department, what unit at UK does this? There's no Deutsche Veterinary Science.
Animal science.
Animal science, okay. So that's part of
Okay, so now from all this data, both manual and automatic, we try to put it together and generate a data set that we can actually use in order to train our machine models and then test our machine models. So what we did is to basically label as day 0 the day in which a cow was diagnosed as having BRD, and then the previous days with negative numbers and the following days with positive numbers. And we also do some segmentation to the data by using window sizes. And so basically for each window, we try to decide if that window is a cow with SBRD or doesn't have BRD. And overall, we have 46 features, and then this is how we decide the label of the window. But what really matters is that we have 3 labels that tells you if during that time window of several days the cow is sick, the cow is healthy, or the cow is what we call pre-sick. So again, remember, one of our goals here is not just to say, okay, this cow is sick or is not sick, but it's try to say if this cow is getting sick before even the vet can tell you, so that you can actually, hopefully one day, start the treatment before, so that the illness doesn't develop and doesn't have such damaging effects. And then we did some standardization as well of the features. So here's what I was mentioning before about the cost. And this is, something that I want to stress during this talk. So when you do this type of, especially for our students, so when you do this type of interdisciplinary collaborations, it's challenging to find problems which are interesting for both disciplines. Okay, sometimes you get a very straightforward computer science solution and you apply it into, let's say, animal science and you get something new, but it's not really new in computer science. Sometimes you get something that is kind of straightforward in animal science, you apply in computer science and you make something new. So it is kind of an exercise to try to find, for example, in this case, a computational problem which was relevant, at least in my opinion, to study. In this context, this was not just, okay, let's get one of these machine learning algorithms and apply it, okay, we are done. So it should be an effort that we try to do in order to find relatively significant problems in both domains. Okay, so for example, the problem that we start looking at here is how much does it cost to collect these features? So let's not just look at all these features and try to do our inference, because each of these features requires you to buy, if it's an automatic feature, a certain hardware, and to use that hardware. Or if it is a manual feature, so it means that maybe a vet needs to come there and perform certain exams. And the more exams you perform, the more it costs, because the more time is going to spend at your farm. So for example, here there are some numbers, real numbers of what it would get for the cost. For example, to buy a weight scale that it costs about $900, but just to buy it, but then use it doesn't have a very significant cost, except the time that someone needs to get the cow, put it on the scale, and then put it off the scale. To perform an ultrasound, a vet will cost $108 an hour, plus the $90 cold fee, plus of course the multiplied by the time of cow, the number of cows that you want to be checked. And also the grain feeder, for example, is a very high startup cost of $500, but then a daily cost per cow is only $1.62. So all these features that may look like equal from an initial perspective, actually they have very different costs. And so here we especially focus on these 2 types of costs. One is what we call the startup cost, so how much it costs to get the equipment to perform that exam or to collect the data, and then the other is what is the cost, the daily cost per cow of actually collecting the data. And so additionally, features are organized in groups, meaning that once I buy, let's say, an accelerometer, then that accelerometer can give me a lot of information, such as the number of steps, how much the cow is laying down, etc., for free, if you want. So once I buy it, I get all this information, all these features together. So features are organized in groups, and once I pick one feature in that group, all the other ones are basically come for free. Okay? And this is kind of a different characteristic that sometimes you don't see in standard modeling of machine learning problems. So of course these costs are kind of assigned to each group. And so, additionally, the last challenge is that even if some features come for free, it doesn't mean that you need to pick all the features in that group, because sometimes they may penalize accuracy instead of helping accuracy. And so, of course, we need to try to find what is the best set of features that provide the highest accuracy within the budget that we have available. And that's the computational problem that we define. And here is formalized, just to give it a little bit more clear definition, but the idea is that if you want to maximize the accuracy using whatever machine learning algorithm you like, where S is the set of features that you consider, and then you have two budgets, one is a daily budget and one is a startup budget. And of course, all these variables basically tells you model the constraint that I told you before. Okay, so basically, if you pick one feature in one group, then the other one have cost 0 once you pick one. Okay. And of course, each feature has got a daily cost and a time cost. But the problem is pretty straightforward. We proved that if this function is basically a modular function, this would be easily turned into knapsack. I guess you can see as well. But I mean, generally, this function is not only not modular, but we don't even know what it is, right? Because here, if you use, let's say, neural network, you get a certain function. If you use random forest, you use another function. So it's very hard to predict, given an algorithm and a set of features, what would be the accuracy. And there are some works that use, for example, entropy to try to characterize how meaningful is a certain feature compared to others. And of course, I mean, those are valid approaches as well. Yeah.
So I understand one side of it, but there's another side which is not present in the model. Getting certain level of accuracy saves you presumably money, and this aspect is not in the model. In other words, do we really need to optimize for the best possible accuracy if half as good accuracy, which is much, much cheaper, will give you only 10% less in gain?
I mean, this is a great point. Of course, it would be a different formulation, right? Instead of maximizing accuracy, you want to minimize the cost with accuracy as a constraint, for example. But
the point is that this one somehow is missing from the...
It's missing, but my understanding is that there is still no knowledge of what would be the economical gain of a certain accuracy. Like, nobody knows.
Yeah, I know.
It's very hard to model, right? So, but then I mean, the problem would be very meaningful. It's just that then it would be hard to know what that function is. Okay, then of course we propose a heuristic in order to solve that problem, given its complexity. And the heuristic is relatively simple. This is what we call epsilon square greedy algorithm, in which basically we have two thresholds. What we try to do is try to explore the set of features, and in order to do that, we try to either have a sort of what we call random action, which basically means you are trying to explore some feature that you haven't seen before, and you can try either to add it to the current set or randomly remove it to the current set, or you try to have more a greedy approach, in which you basically select either you add the features that would provide the maximum increase in accuracy, or you remove the feature that would provide the minimum decrease in accuracy. And you basically start running this with this epsilon that changes over time. Eventually it decreases, and when it reaches low values, this basically turns into a pure greedy algorithm, and so eventually it converges and stops. And I guess, I mean, it's pretty easy. We don't need to go through the details, but that's basically how the algorithm works. For the machine learning part, so here I want to stress how even just collecting those data was so hard that one would say, oh, but let's just try deep neural networks. Yeah, but how do we train such a giant network when the cost and effort to collect data for just 406 cows for 15 months was ginormous? We just do not have the data. So we tried a bunch of algorithms, as I'm going to show you later, but the one that we picked eventually was just a simple k-nearest neighbor approach, which basically maps each data point, so a cow in one day in the space of the features, and then we use the k-nearest neighbor and majority voting in order to determine if a cow is sick, not the distance between points. I guess more or less everybody is familiar with these things these days. So first we looked how KNN would perform with other ones to see if was the best choice. And so we compared with random forest, support vector machine, and linear modeling, and it seemed to achieve the better performance. performance among those. Also, we try to see what would be the best value of K, and so K equal to 7, and the window size means the number of days that we consider 10 would give the best accuracy, even if these are more or less simple. Of course, the more you reduce this, the more you reduce the complexity of the algorithm. And so we select KNN with both three algorithms, including misunderstanding and Gaussian kernel. These are the parameters that we use for our algorithm, and then we use the data set 70% for training and 30% for testing with 10-fold cross-validation. So in these results here, you can see over time, so the algorithm, the different iterations of the algorithm, how the number of the selected feature changes, and how the accuracy also changes. Of course, what the algorithm does is remembers what is the best set that it saw that provided the highest accuracy, and that would be the one that is returned for output. So the one that I think here is probably this one here. That was the highest. I mean, what we can show is that in few iterations, we are able to actually find a very good set that provides good accuracy. Then the first question that we try to answer is, can we determine if a cow is sick? So here we are just looking at cows that are sick or cows that are not sick. If you give me a sample of a cow that is sick, can I tell you this cow is sick or not? And so here we consider different startup budgets, a low one, medium one, and high one, and then we change the daily budget. Look, this number for daily budget may look small, but first of all, they are daily, and second of all, they are per cow. So, when you multiply, they can go high as well. And here we have the accuracy of our approach as well as the comparison approach. We clearly do better. And it's interesting to note that even just low startup budget, but high daily budget, we get pretty high accuracy, determining if a cow is sick or not. And of course, things get better as more money we put into it, which is kind of straightforward. Then we try to determine, can we tell that a cow is getting sick before the vet told you that that cow is sick? So here on the x-axis, you have how many days before diagnosis we can tell that if it's sick or not. So of course, the more you go backwards in time, the harder it gets, because the cow was showing less and less symptoms, and eventually no symptom, right? Because the cow was perfectly fine. Okay, so here we also consider a low budget scenario, medium budget scenario, and high budget scenario, and these are the different features that have been selected by our algorithm. And when the budget is low, really, we can do too much. Because you're flipping a coin and telling you, yeah, sick or not sick. But as you increase the budget, things can get much better. For example, here we can get like 3 days before, we get almost 75% accuracy in telling you that a cow is going to get sick. And here, I think even better, we can do like let's say 4 days before, we can say almost 75% or something like that the cow is getting sick. Of course, the closer you get to the actual day of the diagnosis, the easier it is, because the cow behavior has changed significantly, and so it's easier for us to tell you what it is, but it's also less useful, because 1 day before, there is not much different. It's starting antibiotics, so the more you go back in time, the more useful it is to start the treatment.
So,
Yeah.
this data, I don't fully understand how it went. You have 106 cows. There is, I don't understand how you can collect data for A, B, and C. How do you control for the past?
Sequentially?
What?
Sequentially, so first you collected for A, and then for B, or did you just run your algorithms ignoring some of the...
Yeah, we have everything for every day. So here we run our algorithms, the algorithm tells you these are the features that you can select from this budget, and then we see what accuracy we get for the subject. Okay, so you basically ignore it. Yeah. Anyway, these are pretty promising results. Of course, we cannot say yet how good it is to have this 75% accuracy, which is something that Eric was asking before. But hopefully, in the future, this could be some technology that we use in order to corroborate and help vet in starting the diagnosis before it actually shows. So these are some future work. I don't know how late we are getting. But so we are definitely trying to also look at more challenging scenarios. So for example, trying to do training and testing on different subjects, or training and testing on different farms, because now we have all the cows stay at the same farm and are the same subject. So that would be a factor that makes our job easier. And also try to see, to prevent an outbreak before it occurs, because as I said at the beginning, this virus can actually spread among cows, so you want to prevent an outbreak before it actually happens. So Enrico is also extending this paper in order to try to detect if a cow is going to become chronic, so that, again, can be treated earlier in order to prevent the chronic disease to happen. This would be an extension of the paper, hopefully it will something soon. And then also there are other open problems. For example, I didn't know, but calves actually have personalities. And this personality may then affect their productivity, their behavior inside the farm. And there is this little video here. Let's see if this works.
Probably calves.
So they interact, this sort of interactive environment with different objects. We can record how often they use a certain object, on a certain day, how long they play, and so that can be used in order to infer their personalities. And for example, improve the environment for them, or how to run for them here, etc. And also, another idea is to design algorithms that can tell you if a cow is going to diarrhea. It's another, of course, illness that you may try to predict due to the changes in behavior of the cow. They are super cute. Okay, so I just want to conclude with some lessons learned during this type of interdisciplinary collaboration. So the first suggestion that I have for everybody who wants to work in this thing is to work with domain experts. Okay, as computer scientists, we tend to oversimplify things too much, try to have an abstract view of what the problem is, and then try to just solve it. And because often, we have a lot of solutions, but we don't have a real problem for those solutions. So we try to, force the problem what we know how to solve. And it's a tendency, I have it myself, but if you work with domain experts, you actually realize that things are more complicated, or maybe that some things are meaningful and some things are not meaningful. And I think Enrico here can testify how many discussions we had and he had with the colleagues in animal science in order to understand what was interesting in their domain and meaningful in their domain and what it was not. Also, obviously having a data set doesn't suddenly make you an expert in the domain, it just provides you some data. And as I was mentioning before, it's very unlikely to make a single paper contribution in both fields. And sometimes it's actually good that you end up having papers in other fields with maybe a smaller contribution in computer science, and then papers in more computer science venue which have maybe less of a contribution in their domain, but more of a contribution in our domain. And that is totally fine. But it is definitely a challenge also to identify, as I was saying, computational problems that are have either they are meaningful in the computer science domain or meaningful in their domain. Then another challenge is to, okay, we come up with all these cool technologies, but are farmers going to use it? And there is a lot of stress on this. Also, for example, from NSF, the Smart and Connected Community proposal, and other ones as well, not proposal program, other ones. So we need to try to involve communities to try to understand what their problems are. So maybe we can come up with a super cool solution to a problem that maybe they're never going to care about, or maybe they have that problem but they are not going to use our solution because maybe they're skeptical, or maybe because it's just not convenient for them, it's too difficult to use, etc. And so, we have some collaboration with social scientists that are trying to look in those aspects as well, and there are many projects these days that have this interdisciplinary collaboration, not just with, let's say, animal scientists, but animal scientists, computer scientists, economists, and social scientists, in order for all together try to understand what's a comprehensive solution that will help the community and not will just help us publishing papers in it. That's what we like. And then finally, one challenge when you do this type of interdisciplinary collaboration is try to all speak the same languages. Like these people do not know what an algorithm is, they don't know what complexity is, they don't know what an NPR problem is, and also we don't know what, for example, all these type of illnesses are and how they develop and what. So we really need to try to sit together and try to understand each other and learn some terminology of that domain, and they learn some terminology of our domain, in order to finally speak the same language and produce something. And this takes time. Okay, I mean, I tried at least in 2 different domains, and maybe 3, and then every time it's a learning process. Okay, before you actually are on the same page and able to deliver something that is more or less. Okay, and this concludes the talk. These are some of the publications that we have in this domain over the years. And thank you very much for coming.
Any questions?
Your 8 pizza is fun.
Well, before we have pizza, you opened up with like the birth and death rates in the world population. Do you know what is responsible for the explosion in the world population?
Sex.
Sex. Very good, very good.
Is it one of the leading causes?
It is agriculture.
Fertilizers.
Fertilizers enabled it,
Yes.
but it is the distribution of energy. And it's specifically the distribution of energy in high fructose corn syrup. And you can do that without fertilizer. Yeah. So, and you can't do that. So that was in the 40s. And also the distribution of it. So it was the United States shipping high fructose corn syrup all over the place and caused the population explosion.
I would say it's also antibiotics and medicine. I was going to ask, how is BRD treated?
Antibiotics.
Which means that there is a long-term cost to overtreating.
Right.
So is the sediment profile for BRD similar enough across cow species that you'd be able to use a similar model for all species, or would you like get a separate data set from each one of those across the data?
I mean, I would say this is an open question. I mean, now we don't even know if it works across different farms with the same species. So I don't know. And I mean, it's a very good question in terms that if you want to turn this into a product that someone can buy one day, you need to have it pre-trained and be able to work. And we actually had some discussion having something that is kind of an online learning in which you just deploy it and then it learns the behavior that your cow has, and then try to understand if that behavior is changing over time, and then see if this could be something that's more flexible, because otherwise you need to have specific training for every type of, but don't know how generalizable